Hey folks, today we're going to be wrapping up our discussion of electron configurations and electron orbitals. If you remember from our last video, we found out that electrons can only exist in very specific locations around the nucleus of the atom. And those locations were divided up into energy levels, energy sublevels, and orbitals. And the order of the orbitals then was pretty important, and this is the list that I've shown across the top here, from 1s up to 7s. But when you look at this list, it's kind of long and awkward and difficult to remember. So today's video, I'm going to go through just a couple of shortcuts how you can figure out the order of the orbitals if you ever need to figure out an electron configuration. The first one is if you ever need an electron configuration, you don't have any other tools around, you can always make this little chart to fill it out. You start on the left-hand side of your page and you just make a column listing 1s down to 7s as I've shown here. Then you go over to the right and you make another column for the p's, 2p down to 6p like this. And then you can go over to the column, put in the 3d's or the d's and the f's like this. Then to figure out the order of the orbitals, you just work your way through this chart, and there's a specific way you do it. We're going to start on the upper left there at the 1s and work our way down. And the goal was if you're ever in a particular spot, if you can move down and to the left, you do so. But if you can't move down and to the left because there's nothing over there, then you got to go over to the right and work your way down again. So the first one would be the 1s. There's nothing down and to the left, so you go down to the 2s. From 2s, there's nothing down and to the left of 2s, so you go over to the next column to 2p. From 2p, there is something down and to the left, so you go on down to the 3s. From 3s, there's nothing listed down and to the left, so you go back over to the right, 3p, and then 3p does have something down and to the left, and that would be 4s. So this would be the order for the first 6 orbitals: 1s, 2s, 2p, 3s, 3p, 4s. Now, from 4s, this is where that energy overlap that we talked about in the last video begins to show up. From 4s, there's nothing down and to the left on our chart, so we go all the way back up over here to the 3d level. And then from 3d, we can move down and to the left, so the next thing would be the 4p and then the 5s. When you get to the 5s, there's nothing down and to the left, so you got to go all the way back up over here to the 4ds. And now there are things down and to the left of 4d, so after 4d, the next orbitals would be 5p and then 6s. All the way back up here to 4f, and then 5d, 6p, 7s. And so if you go through it in that order, it will give you that list of the order of orbitals that we have up at the top. And the question then is, you might be asking yourself at this point, well, that may be handy for figuring out this order, but why would I ever need to know that? Why do I need to know the order of those orbitals? And the answer is, later on as you continue in chemistry, you will learn that if you know the order of the electrons or the arrangement of the electrons inside of an atom, from that you can figure out a lot of other handy stuff. Like you can figure out how many chemical bonds a particular element will form. You can figure out how it will form those bonds, will it share electrons, will it gain electrons, will it lose electrons. You can figure out the number of bonds that it will form. You can figure out characteristics about the molecules that will form from those atoms. So a lot of stuff can be figured out if you know the electron configuration and the order of the orbitals. And so this is just a handy tool that will be useful to you later on when you have to learn how to do those things. Okay, so the next thing, another really handy tool for figuring out electron configurations, is the periodic table of elements, which you're probably familiar with by now. It turns out the periodic table of elements is also based upon the electron configurations. And so you can use it to figure out the order. On the periodic table, if we start up at the top, the lowest energy would be the 1s, and hydrogen and helium have electrons only in the 1s orbitals. So if we just kind of read across this thing, this row corresponds with the 1s orbital. Then if we just kind of read our way through it, go back to the left and work our way down, the next thing would be the 2s. Then we read to the right, next section, there are 6 atoms there that correspond with the 6 electrons that go into the 2p sublevel. Then we go back and begin again. We're at the 3s, then the 3p, then the 4s, and we're at that spot where the orbitals begin to overlap, or the energy levels begin to overlap a little bit. And then after the 4s, The next section would be the D section, and you'll notice that there are 10 elements in this part of the periodic table as you go across. That corresponds with the 5 d orbitals. Remember, orbitals each hold 2 electrons apiece. So 5 orbitals times 2 electrons, that's 10 electrons in the 3d section. Then the 4p would be next, then the 5s, then the 4d, then the 5p, then the 6s, and then there's something that you got to kind of watch out for. On most periodic tables that look like this one on the screen, there are 2 rows of elements down across the bottom that I've got labeled 4F and 5F there. Well, those are called the lanthanide and the actinide series, and if you count, there are 14 elements in each one of those rows across. And that 14 is significant because that corresponds with 7 orbitals. And remember, the F orbitals, there were always 7 of them in a sublevel. And they fit right here into the periodic table. If you look at the atomic numbers on the periodic table, there will be a gap between the 6s and 5d section there, and that's where those F's fit in. And so normally they pull those out and kind of put them below the periodic table to save room. But occasionally you'll find a periodic table where those F group will fit up there between the 6F, or the 6s rather, and then the 5ds, which we'll show next. So after 6F, the next group would be the 4F, then the 5ds, then the 6p's, and so on until you get the whole order. Now, once we know how to put these things in order, well, how do you use these tools to figure out the electron configurations of a specific element? Well, suppose we've got an element like this. Suppose we've got boron, and we want to know its configuration. Well, boron is element number 5, and it fits right here on the periodic table. So all you do to figure out the electron configuration, I'll use the periodic table, you know that all the subgroupings before boron are completely filled, and boron's group, which is in the 2p sublevel, is partially filled. So we know the 1s group up here, that's completely filled. The 1s2 is there. Then the 2s group before boron, that's completely filled. So 2s2 is full. And then in the p level, the second p, 2p where we are, boron has 1 electron there because it's in the first one in the 2p, so the last part of electron configuration for boron would be 1s2, 2s2, 2p1. And if you add up the superscripts for boron's electron configuration, you'll see they add up to 5 because there are 5 electrons in boron. Let's run through one more for a little bit bigger element. Let's take a look at zirconium. Zirconium is element number 40, and it fits right here on the periodic table. So if we go through the same process that we did for boron, we know that all the sublevels before zirconium are completely full. So everything before the 4d sublevel is completely filled. The 4d sublevel will be the last thing in zirconium's electron configuration, and it will be partly full. So we know the 1s completely filled, so the 1s2, that's going to be there. We know the 2s is going to be completely filled. In fact, we know everything all the way up through the 5s2 will be completely filled. So we can go on ahead and put in the superscripts and for full orbitals for all the way up through 5s2. And then for zirconium, we know we've got to go just 2 more spots over in the 4d level. So the last thing then for zirconium will be 4d, and it will have a superscript of 2. So that's the complete electron configuration for zirconium. And again, if you just add up all those superscripts, you'll see that they add up to 40 because they show all the electrons for zirconium. So that's how you do it. That's how you figure out the electron configurations for elements. So now that you can do that, you can use that tool later on as you begin to learn some of these other characteristics of atoms. So we'll see you next time. Have fun in chemistry.